Okay. And I assume homework assignment was too easy. I'll probably, I just took a look at it. There were some questions that came in. I think it was too hard, probably. You didn't have, theoretically, it was possible for you to do some research and figure out how to do a few things, but I'll probably give you the weekend off. It was probably too hard of an assignment, I think. So I wrote it, so we're going to go through it. So now the positive is I think there's some good stuff in there that's going to help us look at a couple of things, but some of the extraneous things made it a little bit, my intention was by taking the powers off, it would make it easier. But actually some of the things that would have been trivial in Java, like converting an int or string to an int or string to a double, there's functions for it in C++, but we haven't really talked about them. You can go and do some googly stuff, but let's go through it and we'll look at it, and I'll just give everybody full credit on the homework. So if you didn't turn it in, turn something in, and then I'll give you a reprieve over the weekend. Sound good? All right. Up on the screen here. So this is the same code from last class, but I've added to it the solution with the powers. So we'll kind of talk through all the pieces to it. So the only thing I've added is this new function called process output queue. So that's the guy that's going to walk through our output queue. All right, so officially for the homework, we were supposed to go through and basically do everything except not deal with powers. And so you'll see when we go into my code, it's just everything except this one if statement. So my one if statement is the thing that I was trying to explain last time in terms of how to deal with powers. And actually in the end, I think maybe the code version of it explains it better than doing it in the slides. So, because it really actually isn't bad, it's just, it is what it is. So let's take a look. So here's my process output queue. I created 2 extra stacks, just like we had last time. We had our math stack, and I had that extra op stack for dealing with our powers. All right, and this is kind of this dude here. If I just back up. So as we're walking through our output queue, we are pushing things onto the math stack, onto the math stack, onto the math stack until we hit an operator. Okay, and then we do some stuff. All right, and when we hit any kind of operator that's not a power, we do relatively easy stuff, right? We just do our math. But the challenge in this was, okay, I have a linked list of strings and I need to do some math with those guys. Doesn't sound like it should be the end of the world, and there are functions for doing it in C++, but because we haven't spent too much time looking at C++ documentation, which let's call it, it's fine, but it's not as friendly as Java. When you look back at like the 250 class, we do quite a bit of stuff where, we go and look at the documentation and say, this is the documentation says it should work this way. Now we look at the actual code, it works that way. We can kind of do a lot of, theory and proof of it. We haven't really seen that with C++. So we'll look at that a little bit today. It really isn't any more difficult. It's just less, it's not all in one place. You effectively do Google search, convert string to float or something like that in C++, and hope you're getting a library that still exists, something along those lines. And almost all of them do. So it's a lot of the things that are old have just been updated to be more updated. So in any case, let's go and look at the code for this. All right, so start of this guy, as I'm processing my output queue, what am I going to do? I'm going to keep walking through my output queue till I run out of crap. Keep doing stuff until this dude is empty. Nothing earth-shattering about that, right? All right. This guy handles a bug, presumably, that's in our linked list of strings. Actually, it would be in our process shunting yard, because I was still getting actually, I think do I show it in my output? Let me see real quick. Don't get it there, but let me take those two guys off. Maybe it shows here. Yeah, I didn't spend any time looking for it. It's probably a pretty easy fix, but after the minus, I got another empty token. So fix for that. If you see an empty token, rip it off there and just skip to the next version of the loop. A little bit of duct tape, but yeah, reasonable enough, I think, in this case. I didn't do anything with the empty string. I just said, look, if the top of the output queue, the peak, has a length of nothing, I can't do nothing with that. So let's rip them off there and just hit continue, which just takes us to the next time through that while loop, skips the rest of it. Okay. Quick and dirty, because I didn't have time to go and run and look at why this is happening. It's probably something pretty trivial, but that doesn't matter. That's not really the focus of what we're looking at. So that's all that if statement is. That if statement is the duct tape fix for what's it, process input queue. Potentially empty tokens. All right, so really the real logic starts here. All right, so we'd already written a thing last time called isNumber that asks, is the thing at the top of the list a number? All right, and I think if I remember, there was a question, somebody said, well, isn't isNumber means that it's not an operator? I don't remember how we ultimately wrote it, but that's a true statement. But in any case, we're going to peek at the top of the output queue. If we're looking at a number, what do we do with it? We just put it onto our math stack. If I see a number, what do? I push it onto the math stack. I see a number, push it onto the math stack. See a number, push it onto the math stack. That's what we do when we see numbers. Okay, so if I see a number, push it onto the math stack and remove it off of the output queue. So pop it off the output queue, push it onto the math stack. Else if, we'll come back to this in a few minutes. All right, but for right now, this is all the logic for how to handle. Well, this is half the logic for how to handle it, because we have to go back and do it at the end. But because it's right to left, whenever we run into something to the power, we just throw it on this extra stack we created called the op stack and move it off the output queue. We put it somewhere else to deal with later. That's all we do with that guy. Otherwise, I must be dealing with a normal math operator. It's not a number, it's not a power, it's one of those other mathy things. Okie dokie. So the very first thing I can do, and this has to do with the powers. Before I'm allowed to do other mathy stuff, I have to deal with the powers. All right, so I'm not allowed to do normal mathy stuff unless this secondary op stack is empty. So if I keep going through here and we hit the multiplication, that's not a number, not a power, normal mathy stuff. I know that I want to do 4 times 2 to get me an 8. But the first thing I can do, the first thing I have to do before I'm allowed to do that math, I have to say, is there anything to do in here? Right now, the answer is no. Nothing to do in there. Okay, that's what I'm asking right here. While there's something in the op stack, deal with that something. As soon as there's nothing in the op stack, this is where I do my math. Okay, so for right now, we'll just keep going through our example here. There's nothing in the op stack. So I'm free to do my math. All right. What do I do with the math? So here is that function. So if I have a string, so math stack pop, these are our numbers. Well, there are strings that live at the top. So notice I'm calling it B, then A. So I'm kind of reversing them. So I'm popping a 2 into B. I'm popping a 4 into A. But these guys are coming off as strings. I need to convert them to floats. Okay, not ints, because there's no guarantee, especially with divisions, there's no guarantee that we're going to be dealing with whole numbers or positive numbers for that matter, right? Now, could we have written our own functions for converting floats to strings to floats? Sure. And it's not like the end of the world type thing, but it wasn't really the focus of the assignment. Certainly, I mean, in previous classes, we've written like string to decimal or something like that, where we have a string representation of a decimal number and convert it to a numeric version of a decimal number for integer. Same thing that integer.parseInt does in Java. And that's not too bad. You basically just need an extra if statement to handle positives and negatives. But floats are a little bit more complex. Not the end of the world, but we presume that most languages probably have a little tool built into them that allows us to do that. So maybe a mentality that if there's something you're going to take away from this is a mentality as you were going through this assignment, you might say, hey, you know, I wonder, does C++ have a convenient way of squeezing a number out of a string? Let's go look and see if there's a function. There's a bunch of good stuff inside of the standard library. All right, and that's where this guy lives. And actually the functions that we're going to look at here, they've been around forever and ever. They worked on old style strings, and they've been updated to work on our new style strings. So if I say C++ string to float, for example, does this give me the, I think this was the good reference one I liked. Yeah, so this is the standard library, and there's a function here called S2F, string to float. And what you do is, in the simplest form, you give it a string, no other parameters. You don't have to tell it what the base is and stuff. If you remember in Java, you can say, hey, I want to convert something. I want to say integer.parseInt, and you could, there's two versions of it. There was one version where you just pass it a string and it assumed that it was a decimal number. And then there was another version where you say, hey, you know what? That's a base 16 number. Do it anyways and make it work. Same thing's true here in C++. You know, so they show you some examples of it, but this is, you know, it takes some other optional parameters. Here's a so converting a string to a float, S to F, pass it the string. If you want to do a string to decimal, it's S to a string to double is S to D. String to int is S to I. So S to I is equivalent to integer.parseInt. But notice that it is a function that operates on strings. It's not a function that's owned by strings. So this isn't a function that we're not saying str.toDouble or toInt or toFloat. We're saying, hey, here's this piece of machinery I have called S2F, and I throw a string into this guy and he gives me the float version of that string. This is a secondary piece of equipment, a function that knows how to work with strings. Okay. So what am I doing here? I'm getting the floating point version of my string at the top of the stack and the floating point version of the string that's now the top of the stack. I'm popping off 2, putting it into a variable called B as a float. I'm popping off 4, putting it into a variable named A as a float. Then I'm going to ask some questions about what this operator is. Is the operator plus sign? No. Is the operator minus sign? No. Is the operator multiplication? Yes. Answer is equal to A times B. In that case, the fact that I put him in A and B didn't matter. It matters with subtraction and division. We got to make sure they're in the right order. But addition, multiplication, doesn't matter, but we're still handling them correctly. Okay, so we get down here. We go ahead and burn past our operator. We don't need to put it anywhere. We've already done the math. So we just had a multiplication sitting there on the output queue. We said, okay, I've done my multiplication. I no longer need you. Pop, I'm not putting you anywhere. You're just gone. All right. And then we have our answer here, which is currently a double. All right. So it's a floating point number. And I'm going to put that back onto my math stack. My math stack is a linked list of strings. So even though I have it, I just did the work of converting the two top things into ints or into floats, did some math with them. Now I want to store it again. I got to turn it back to a string. So we have another function here called toString. So if I come up here and I do if I say double toString C++, we'll see there's more stuff in the standard library. And we have all these toString ones, and these belong to this newer style string class. Well, they operate on the newer style string class. They don't belong to it. They belong to the standard library. So I call a function. I have a second separate piece of machinery called toString, and I can pass it basically any of my types, and he will turn it into a string. Now, we can accomplish this with concatenation, but the issue we run into with that is we have to, when we use just double quote, C++ thinks that's an old style string. So I have to start dealing with typecasting and things like that. Because in Java, what would we do? We would just say, oh, you got your answer. So if we were writing this in Java, we would just come in here and we would say, there, empty string plus answer. That's a string version of answer. Done. Easy peasy. Now you can accomplish this in I think you can do something like if we say string s is equal to the empty string. Then we could say s is equal to s dot append answer. I think that'll accomplish the same thing. We can build a string out of it. You probably could massage it into a situation where you can use the plus sign for the concatenation operator to do it. Although I don't know if that operates on an int or a float or whatever on the other side. So, but I think this would probably pull it off. I don't think this will pull it off. It's not defined for integers. But here you can even see it's kind of interesting. It's showing how these libraries have evolved over the different versions of C++. It's not any different than Java. It's just less friendly because it's changed over the years to try to evolve into more modern languages. So in any case, we'll use a built-in function that knows how to do things to strings, because presumably it's not overly convenient to do things to strings on our own, right? So we'll call toString, we'll pass it the math, the answer to our math problem we've done, get it back into a string format, push that string back onto the math stack. So we pop the 2 into B, pop the 4 into A, perform multiplication. So for the moment, these two guys are in variables A and B. We perform the multiplication of 2 times 4. Answer is 8. Push the 8 as a string back onto the stack. Okay. Then we keep going. So this hits the end of that. We loop back up. Output Q still has stuff on it. What do we do? Look at the next thing. Right here, is that a number? Yes, it is. What do we do with numbers? We push them on there. Loop back up. What do we do? Next guy's a number. What do we do with numbers? We push them on there. Loop back up. What do we do? Next guy's an operator. Well, he's not power. He's a normal math operator. So now we got to go and do some math. But before we're allowed to do math, we need to make sure that there's nothing inside here that needs to be cleared. So we look at our op stack. That's what this code right here says. Right here. If I'm looking at a normal math operator, so if it's a normal operator, I'm going to take a look at my op stack. And if it has a count greater than 0, I got to do some stuff. We'll see an example of that in a few minutes. Otherwise, I'm sitting right here. Time to actually do my math. So what does this say? Same thing as we just did a minute ago. I'll pop the 5 into a B. I'll pop the 1 into A. I'll do my math. A minus B. 1 minus 5, which gives me a -4. Convert that back to a string, push the -4 back on here. That's what's happening right in here. We got the 5, we got the 1, we saw it was subtraction. We did 1 minus 5, gave us a -4. We pushed that -4 back onto the thing as a string. Get rid of that line I added. Okay. Go back up. We hit a 2. It's a number. What do we do with numbers? Push it on. We hit a 3. It's a number. What do we do with numbers? We push it on. Now we hit a power. So really, the code we currently have written, in fact, let me just, if we just pretend like we don't have those powers here for a second, we would have been missing this 2, the 3, the power. We would hit the divide. So we wouldn't have had this. Instead, we would have hit the divide. We would have popped the -4 into B, the 8 into A. 8 divided by -4 should give me a -2. 8 divided by -4 gives me a -2. Push the -2 back onto the stack. Then we get to the addition. What are we going to do? We'll pop the -2 into B, the 3 into A, do the addition. We get a 1, push the 1 back onto the stack. All right. Now this guy is empty. This stack has exactly 1 thing left on it. Our answer's at the top of the stack. And we're going to see that again through this example. All right. So the logic I've given you here already works for not having these guys, what we've already been going through. But we'll go ahead and do it with these guys. So I ran into a number. What do I do with them? I push it. I ran into another number. What do I do with them? I push it. I run into a power. So this is our special case. And it's special because powers are done right to left. So we look at the code. If I'm looking at a power, what do I do with it? I go ahead and pop the single value at the top of the math stack onto my op stack. So I'm going to pop this 3 onto here. Push it onto there. I hit another power, and well, I don't do anything else in here. This just burns past that power. I don't need to store the power symbol anywhere because I know that the only things that live on the op stack are things related to taking something to a power. Okay, so now I've burned past this guy. Next guy I read in is another one of those. What do I do when I read in a power? I pop, push, burn past the power. Keep processing the output queue. Next thing, I hit a divide. I want to do math, but we need to make sure the op stack is clear before I can do math. So let's go and look at what do we do to clear the op stack. If I'm in this else, that means I intend to do math, but I have to make sure the op stack is clear first. So as long as I have something in the op stack, well, the count is greater than 0. Right now, the count is 2. I have 2 things in there, right? This is my op stack right now, 2 and 3. What am I going to do? I'm going to go ahead and extract the power I'm taking something to, where I'm going to pop the top value off the op stack. There's 2. I'll pop that into a float, so I have that number. Then I'll pop the single top value off the math stack, my -4. I want to take a -4 to the second power. That's the math I'm about to do. This is the power. This is the thing I'm taking to that power. I give myself a starter value. Now, there's probably a function for taking something to a power in C++, but I just wrote a loop. You know, do something power number of times. So -4 times -4, just multiply it together so many times. All right, so I have my power stored in a variable. I have my number stored in a variable. Really, this potentially could have a bug associated with it. We really should make that a double. Otherwise, I would have truncated, like if it was -4.2, for example, it would have truncated that to a -4. All right, so we'll take the value that's on the math stack, pop it out. I'll start off, again, I probably should make this a double. And we'll just loop through and I'll multiply whatever val currently is by that number. I'm going to do that power number of times. So val is going to hold, in our case right here, 4 to the second power, which is 16. That's what val will hold. What do I do with that 16? I push back onto the math stack the 2 string of val. So I've already popped that guy into power. I've popped this guy into, what do I call it, num, into num. I've done my math, got a 16, pushing the 16 back onto the math stack. All right. Then I loop back up, still inside of this while loop. Is my op stack clear yet? It's not. So I still have a count greater than 0. So what do? I pop whatever the power is, which in this case is a 3. I pop into num, whatever the number is, which in this case is a 16. I take 16 to the third power, which gives me a 4096. That's what this loop thing here will do. It'll store in val a 4096. And then I take that 4096 and I push it back onto the math stack. Pop into power, pop into num, do the math, push 4096 back onto the math stack. Okay. Loop back up. Do I still have stuff in my op stack? I don't. He's finally empty. I've cleared the op stack, so now I'm allowed to do normal math. So now I'll go do my normal math. Pop this guy into B, pop this guy into A. I notice I have a division, so I'm going to say A divided by B, 8 divided by 4096 is this guy. So we've popped into B, we've popped into A, we've done the math, stored it in an answer, pushed the string version of it back onto the math stack. Is our output queue empty yet? Nope, not yet. We read in the plus sign. It's a normal math operator. We want to do math. We need to make sure our output queue is clear first. It is, so we don't have to do anything extra. We pop this guy into B. We pop this guy into A. We notice we're going to do some addition. We get our answer, which is that guy, pushing the result back onto the math stack. Loop back up. Is there anything left in our output queue? There's not. So we're done processing our output queue. We do need to have one last little pass just in case the nature of whatever expression was put in happened to have powers at the very end. I could still have a few things sitting on my op stack here. If depending on where I was taking powers, if I didn't have operations after I was doing powers, I would have never had the opportunity to clear that op stack. So before I finally spit out my answer, so down here, this is after I've finished, after I have finished the output queue. I'll take one more look at the op stack. It's the identical code. Good programming practice probably would have said put that in a function. So doing it more than once, don't duplicate code. Let's just call this a whatever. We've already used some duct tape above, so we're just gonna kind of roll with it. But in any case, I'm just doing that same logic again. Clear the op stack, do any power stuff you need to do. Ultimately, you're pushing answers back onto the math stack. The way shunting yard ends up working is when all this is said and done, you will have exactly one value sitting on the math stack, the answer. So we'll return whatever the top of the math stack is, converted to a float, just because I have this guy returning a double. And right now I'm just having him return to the constructor up here. So the very last thing I do is call process output queue, and I just print it out. So I'm just doing it in the constructor. Inside main, I have my string. I can just call shunting yard, and just inside that constructor, he does all the magic. I don't have to call any, I mean, I could design it to call a function to perform the math or whatever, but he just does it. So if I go ahead and put the 2 and the 3 on here, we should see by our answer here, we get a 3 point blah, 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 blah as our final answer. And that's what this guy should give me. There's my 3 point blah, 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 blah. All right, so does that make some sense? Hopefully, as we walked through, you see kind of that truth that all hard problems are made up of a bunch of easy parts, right? So no individual piece of that was overly horrible. It was just kind of getting everything pieced together in the right order, with the caveats that now you have to find these little stupid conversion things in the middle. I mean, the intention wasn't for it to be so annoying to have to go from strings to numbers and numbers back to strings. Frankly, that's actually what made it annoying, the assignment. You weren't able to focus on the algorithm itself, but you could have gone back, I guess, and written your linked list to be a linked list of doubles. That would have solved that would have solved the problem. Yeah, you still would have needed the linked list of strings to handle your operators. But yeah, it is what it is. All right, so go ahead.
I was wondering, can you have in your linked list different data types?
Yeah, you can. And I kind of referenced this when we wrote our original linked list, where you can have a linked list of generic nodes, things that are nodes, and then make string nodes and float nodes and double nodes and things like that using inheritance. Well, no, because you can do it with arrays too. You could have an array of nodes where if you have a node class and you inherit from that node class a string node and an int node and a float node, technically string node, int node, float node, all those guys are nodes. So if you have an array of nodes, that's allowed. I was about to say, unfortunately, C++ doesn't have this, but I bet you they do now. Because we have a nice function inside of Java as well as C# called instance of that allows us to ask a question. Is this object an instance of this class? So you can kind of have an if statement. If you have a collection of nodes where those nodes come in 3 different flavors, you could say, is that guy an instance of string node? Or is he an instance of float node or whatever? Because then you could treat them differently. I'm sure there's equivalent in C++. Actually, this is an old function, a dynamic cast. This creates a void pointer of this type and compares them. It's kind of what makes C++ fun. And it kind of is maybe why it's pretty appropriate for this level class that you already have a year of coding under your belt. Because hopefully, at least for most of the assignments, you're spending roughly the same amount of headache time as you spent earlier, but obviously you're solving much more difficult problems now. But at some point, when you start getting into things like this that read more like stereo and instructions, if you've had enough programming, it's easy to read this. But if you're used to Python paint by number or Java, which has just beautiful documentation, going back to this, it kind of makes you really appreciate some of the more modern languages. You know what? And really what we're seeing here, which I would say is good in hindsight, is that you're seeing C++ kind of trying to keep up with the Joneses, because it is still a viable language because of its speed. It's your fastest object-oriented language. So if you're doing video games and stuff like that, C++ is where it's at. Yet you probably learned in school one of these more modern languages. And now you're like, oh, well, I want to do this, and I want to do this, and I want to do this. Well, somebody wrote the code to do it probably. The issue is you don't have it just in one local library. You know, you have to go and find out, you know, Bob's C++ library that, that knows how to work with, you know, strings in some sort of special way or something like that. So it feels geeky and it's fun and things like that. But I also, so my regret was the assignment was meant to focus on the end of shunting yard, but it ended up having you focus on things that weren't related to the shunting yard algorithm. So it's in the past now. All right. So any other questions about this guy before we just kick it to the curb? We want to get on to our nonlinear linked data structures. Let's see, one more thing. We're at 55, right? Okay, good. When is fall break? Not the end of next week, but it's the end of the week after, right? Okay. So what I'm thinking is that we'll have the exam, because we don't have class Thursday or Friday that week, right? So I probably will officially say we'll have the exam on that Wednesday, but whatever that is, the 22nd, 28th, 20th, yeah. Yeah, we just saw the weakness of masks, right? 2-0. But what I'll do is I'll usually do them online. It's A, it's easier for me to grade, and B, it's probably easier for you to take. Not that I'm encouraging you to do this, but I happen to know that sometimes students ditch out a little bit early for, for breaks. So I'll probably put the exams up maybe sometime late Sunday night or by Monday morning. Take it before midnight Wednesday or something like that. Just so, because I'll probably grade on like Thursday and Friday or whatever. I don't know what my wife's doing for the trip or if we're going anywhere, but whatever. So you'll have some flexibility on time and stuff, but we'll remind me the Friday before. So I guess next Friday, week from today, we'll, that's right, week from today, 2 weeks from today. Yeah, a week from today. We'll go through the slides and I'll kind of point you in the direction of what I think is important, what won't be on there. And again, I want the focus on that exam to be on data structures, not C++ quirks. Okay. So take it or leave it, whatever it is. All right, so let's just spend the last couple of minutes introducing our first nonlinear linked data structure. So we're going to start looking at binary trees. But we won't do an assignment over the weekend, so you can let your wounds heal. Now, what actually happened? Did we actually spend hours and hours on the assignment, or we just say, I'm done? And just gave up? Yeah. Well, I guess in hindsight, that's probably better. I would feel worse if you spent like, I mean, I would be entertained, but if you spent like 16 hours on it, and like, look, I spent 16 hours, my hands are cramping. I broke a keyboard. Well, I broke 2 keyboards. One I threw, the other one was just wore out. All right, so let's look at binary trees. So really, we're talking about nonlinear linked data structures. And this is maybe a fancy-ish kind of way of saying that next node can be more than one thing. You don't just have a node that links to exactly one other node. You can link to, in the case of a binary tree, 2 nodes. And in the instance of an n-ary tree, any number of nodes. And then we're going to also look at graphs, which then get all sorts of wonkiness from, because they climb back up the tree and things like that. But we'll start off with so these are linked data structures that have pointers to potentially more than one next node. So that would be kind of our generic type thing. So if we look at a picture of this guy, so let's look at a binary tree. There's 2 pieces to a binary tree. One is what they look like. And then the second one is the rules that they have to follow. So, and really those are 2 separate things. A binary tree is any tree where a node has at most 2 child nodes, 2 next nodes. A binary search tree, which is really what we're going to be looking at, follows the BST rules for how things are added to the binary tree. And it's not horrific, but we'll see it. But if we start off here, a binary tree, we might have our root node. I'm actually going to accidentally make this one to follow the rules of the binary search tree. All right, so this is the root node. So they call them trees, but it's really an upside down tree, right? So this is the trunk. This is the root of the tree. It has two children in this case, a 2 and a 6. So these are called child nodes. This 2 has two children, 2 and 3. Because these guys do not have children, they are called leaf nodes. Leaves are at the, once you stop hitting branches, you're stuck with leaves, leaf nodes, okay? What they're called is kind of insignificant. That's more just naming stuff, all right? But the idea here is at most, a node can have 2 children. This node has 0 children, 0 children, 2 children, 2 children, 2 children, 0, 0. You can have a node with 1 child. You can have a node with 1 child like this. That's allowed. Okay. So that's what a binary tree looks like visually. Now, to follow the rules of a binary search tree, binary search trees have to do with, have a set of rules associated with them that dictate how nodes are added to the tree. As we're building a tree, things have to be added to the tree in a certain order. The rule is pretty simple. Given a single node, everything to the left of that guy will be less than or equal to that node. Everything to the right of that guy will be greater than that node. Keeping in mind that a tree, binary tree in this case, is actually a tree of trees. This guy is the root node of this entire tree. This guy is the root node of this subtree. This guy follows the exact same binary search tree rules. Everything to the left is less than or equal to. Everything to the right is greater than. This guy is a sad tree. He's a root node with nothing else. It's a leaf on the ground, okay, but he does have a value. And technically he follows the rules because he's only just a root node. Okay, so what we'll be looking at, first we'll look at how do we build an initial tree structure. So we'll build the nodes with left child and right child. So we'll initially focus on binary trees specifically with exactly, well, 0 or 1 or 2 children. Then we'll look at, well, how do I build a binary tree? If I'm giving a list of numbers, how do I build a binary tree to hold those numbers? And what does that tree look like? Because the tree, you could hold the identical set of numbers in a binary tree, and the tree will look different based on the order in which you added those numbers to the tree. Because as we're plotting them in there, as we're deciding where to drop them, where it follows the rules, if you put those numbers into the tree in a different order, you're going to end up with a different tree. And then we will talk about things called something called tree balancing, or if you have bad luck and the numbers just come up in a certain order, you might have a tree that's very like left heavy, right? Or very right heavy. And then we have to start thinking about, well, binary search trees presumably must be good for searching. And if you don't have a balanced tree, your average searching efficiency might be worse, something like that. So then we'll talk about some self-balancing trees like AVL trees, which are nightmares. But what they do is after you've added something following the BST rules, it says, okay, are things out of whack? If yes, let's do some chiropractic adjustments to the tree and rotate stuff to get it into the right balance without breaking the BST rules. All right, makes sense? All right, so we'll do that as our introduction to binary trees. We'll come back on Monday and actually start implementing them. No homework over the weekend. The code, I think, is the same starter code that I'd given you for the homework assignment. If you want to go and check out the code, it is saved. All right, I'll see everybody on Monday.